Sorry, let me actually unmute myself. And then it's going to be roughly 30 minutes. Again, if you stay awake during the class, I think you should be able to solve it in less than 10 minutes. If you haven't studied at all, then it may take a while and might be a little challenging. So what we've learned so far, plus what we're going to learn tomorrow, is the scope of the quiz. And then consider the Thursday and the Friday lecture as kind of the bonus. So yeah, so that's what's going to happen. Well, for today, we're going to be, looking into the implementation of Fourier operators. So as usual, here's the notebook opened in the Google Colab. And for this one, I will change the notebook setting. So here's the edit notebook settings. And then picking the T4 GPU as my hardware accelerator. So after that change, I'm running the first cell. The first cell is really just importing all the necessary libraries, so nothing interesting going on. Now, after the first cell is a brief introduction to Fourier transform. Considering the audience, I will assume that you guys know the basics of Fourier transform. So at the end of the day, the idea of Fourier transform is to, for a given, continuous signal, you want to decompose that into the combination of a bunch of sine waves with different frequencies. So mathematically, this is kind of the transform that we're talking about. So Ft is the signal that is defined in the continuous domain. So that's the original signal. And then the capital F of omega is the signal in the Fourier domain, the spectral domain. And then by computing this integral, we're basically converting this original function f, which is, by the way, defined in the original time domain, into the frequency domain. And then the inverse Fourier transform is essentially the reverse process. So again, here's the mathematical definition. So for those of you who are not so sure or still don't remember Fourier transform, there are lots of textbooks. So any kind of engineering math textbooks should contain the discussion about Fourier transform. So may not be a bad idea to kind of brush up what you learned already. In the computational world, though, computing that integral is not a computationally viable thing to do, which is why we introduced this thing called the discrete Fourier transform, or DFT. So DFT, breaks down that integral into the finite sum of this thing. So xn is a signal represented in terms of an array of numbers, right? And then capital XK is the frequency component after the Fourier transform. So instead of the continuous function, now we have a discrete sequence of numbers, and then that's how we compute the Fourier transform over here. Now, long story short, DFT algorithm, at the end of the day, you will need to calculate the, this exponential of complex number here, right? So that's essentially the combination of sine and cosine. Obviously, computing this in a rigorous manner will require a lot of computation. So what happens in the practical implementation, we use what's called a fast Fourier transform algorithm. So instead of computing the entire set of the coefficients, we're simplifying that, and then FFT obviously, as the name indicates, is designed to handle the Fourier transform of some large signal. So again, I'm not going to go into the details of FFT and the DFT and the difference between the two, but you can understand FFT as some computationally efficient way of implementing Fourier transform. And if you want to learn more about FFT, there's a link to a nice tutorial from which you can gain a better understanding of what's going on. But here, I'm just going to go directly into the example and then show you how FFT is implemented in PyTorch. And then from there, we will see the implementation of the Fourier neural operator using that FFT implementation. So before getting to the neural operator implementation, here's a toy example for Fourier transform. So here's a signal that I generated arbitrarily. So this is a synthetic signal. And this signal is comprised of two sine waves. So we have sine 30 pi and the sine 40 pi. And then, because, we know, like from from what's inside of the sine function. Actually, sorry, I forgot to put t. The sine 30 pi t, and then sine 40 pi t. But sine 30 pi is essentially a signal with the frequency of 15, right? Is what's going on over here, and then sine 40 pi is a signal with the frequency of 20, right? So it's a combination of two sine waves, one with the frequency of 15 and then the other with the frequency of 20, is what you're seeing over here. So since Fourier transform is all about decomposing a function into a combination of sine and cosine, since this original function is already comprised of two sine waves, if our Fourier transform is accurate, then what we're going to see is basically two frequency components, right? One corresponding to the 15 hertz, and then the other corresponding to the 20 hertz. So let's actually see if that's the case. So here, we introduced this thing called the torch.fft.fft. So the torch.fft is a fast Fourier transform module. And that module contains all kinds of functions that are relevant to fast Fourier transform. And one of those functions is the function named FFT. So that's the actual fast Fourier transform. So what we're going to do is to put in the graph form that we just generated, right, into the FFT function, and then compute the x underscore ft. Okay, so that's the Fourier transformed Fourier transformed signal. So that's the coefficient that I was talking about, before the break. And then, after a little bit of, processing, I plot that, FFT result over here. So in the horizontal axis, we have the frequency. The vertical axis, we have the magnitude. And then it seems like we have some, coefficients discovered over here. But then you may wonder, well, we started from two frequency components, right? 15 hertz and 20 hertz. But somehow we have not only 15 and 20, but also 30 and 35-ish, right? So that's because for the real signals, real numbered signals, the Fourier transform will always have this, imaginary component. And because of that imaginary component, we have usually the mirror image of the result if you just naively apply FFT. Okay, so these two, obviously 15 hertz and the 20 hertz, are the actual frequency components that we calculate from fast Fourier transform. And then because of the way that we plot, the imaginary numbers actually capture the mirror image of those two. So if you don't like that, then yes. True. So that's what I'm about to explain. Um, so rigorously speaking, the fast Fourier transform result should be shifted, okay, so that we have those mirror images correctly represented, okay, with respect to 0. So here I used a function called the FFT shift. So that's again inside of the FFT module. And then what that does is to perform a circular shift of the Fourier transformed signal, so that after the circular shift, we have this result where we have the frequencies just with different sign. We get the mirror image. So this is way better representation than what was there previously. But of course, I mean, the original, Fourier transform is kind of redundant because, we get to have this mirror image. And then the negative frequency part is like just the duplication of the positive frequency. So what's the point of doing this, right? So in practice, so this is the real thing. I've been, pretty quick about explaining the earlier part because that's actually not what we're going to use. In reality, in practice, since we're going to be dealing with the real signals only, and we don't really care about the imaginary components of the Fourier transform, we use the function called the RFFT. So RFFT stands for the real valued fast Fourier transform. And in case of RFFT, we ignore the mirror image of the Fourier transform, the imaginary components, and just perform the transformation on the real components only. So if you do torch.fft.rfft, then what you're going to see is what you would have expected initially, where we have the frequency components all 0, except for 15 hertz and the 20 hertz, which is exactly the decomposition of the signal that we first put in, right? So from there, we kind of know that, oh yeah, the RFFT works fine, okay? So it's really just one line, at the end of the day. And this one line, torch.fft.rfft, will convert the original signal into the frequency domain components. And then that frequency domain component is going to be comprised of the coefficients indicating what kind of frequency signals are contained inside of the, inside of your original function. Okay. Now, of course, since there's a FFT and RFFT, there's an inverse of those functions as well. So torch.fft.ifft is the inverse transform of the regular FFT, the one with the mirror image. And then, if you run the IFFT, then you will basically be able to reconstruct the original signal And in this particular case, since the original signal is comprised of 15 hertz and the 20 hertz, and it's quite simple, the reconstruction accuracy is going to be 100%, right? Where we're not losing any signal during the Fourier and the inverse Fourier transform. Similarly, the RFFT, the real valued Fourier transform, has the inverse. Okay, so that's called the IRFFT. So inverse of the real valued Fourier transform is defined under IRFFT. And what you do here is to simply throw in the Fourier coefficients. And then taking that Fourier coefficients, you can calculate the original signal or reconstruct the original signal from the Fourier coefficients. So it's as you can see, very straightforward to use. You just need to put in a signal, run RFFT in our case, right? And then you'll have Fourier coefficients, and then on that Fourier coefficient, you do your stuff, and then after some transformation, you throw that Fourier coefficient into IRFFT, inverse RFFT, and then as a result of that, you can reconstruct the original signal. I just told you IRFFT is the inverse of RFFT. So for the real value function, there's no difference between RFFT and the original FFT. Yeah, we're just skipping the imaginary part because if you have a real value signal, you don't really need the imaginary components because the imaginary component is just a mirror image of the real value component. So, if there's a guarantee that your function is real valued, then you don't really need that imaginary components all along, but just keep the real value components, and in that way you can make the computation slightly more efficient. Okay? I stands for the inverse. Yeah, so same thing. If you ran the real valued Fourier transform, then you have to do the inverse of the real valued Fourier transform. So if you constructed the frequency component using RFFT, then you have to use IRFFT. Those are the pairs. And then if you use the original Fourier, the full Fourier transform, then you have to use the full inverse Fourier transform. So that makes sense? Okay. All right. So that's really what you have over here. Here's another example. So I generate a signal that looks like this. So the sine wave combination, although it's kind of simple, but not too fun, right? So here's a little more interesting example where I have sort of a bell curve, but with lots of noise added, right? So here we're going to apply RFFT. And then as a result of that RFFT, we get the coefficients that looks like this. So the frequency zero component, the constant component, is pretty big. And then the rest of the components are, kind of small, but you can see a little bit of fluctuation, right, in the frequency components. Now, the original signal is decomposed all the way up to 60 something hertz. Okay. That maximum frequency is defined by the resolution of the signal. So I, as a matter of fact, have the sampling rate of 128 hertz, okay? And for a signal with 128 hertz, Fourier transform will calculate the half of that frequency. That's the maximum frequency that you can sample, right? So that's why after the decomposition, we have up to 64 hertz, okay? Those are the frequency components that we calculated. Now, out of those 64 components, what you could do is to take the first 10 components. So first 10 components are the components with the relatively lower frequency. And using those first 10 components only, I'm going to be doing the inverse of RFFT. And let's see what happens. As you can imagine, since we truncated the high frequency components, all this jiggly pattern in the original image is going to go away because the jiggly pattern essentially corresponds to high frequency components. And as a result of running the IRFFT, the yellow curve is the reconstruction of the original signal, and then the black curve is the original curve, original curve. So again, if I used all 64 components, frequency components, then I would be able to reconstruct the exact form. But since I only used the first 10 components, this is, in signal processing, what's called a low pass filter. So you're passing only the low frequency components and then ignore the high frequency component by setting them all to 0. And in that way, you can kind of filter out the noisy high frequency fluctuation like this, and then you can obtain almost a perfect bell curve, right? After the noise removal. So this is kind of in relation to what I said, almost to the end of the neural operator lecture. Neural operators tend to be more accurate and more robust to noise compared to other, usual deep neural networks, because all this kind of, jiggly patterns naturally goes away by the virtue of taking the first few components of the frequency components. Okay. So that's really a quick demo of the PyTorch FFT module. Okay. And if that makes sense, what we're going to do now is to use that FFT module to define what's called a spectral Comp1D layer, or Fourier neural operator layer, if you will. Okay. Well, actually, this is not, I wouldn't call the Fourier neural operator layer. It's actually that little box that we saw in the lecture slide. Give me 1 second. Yeah, this part over here, this yellow shaded box, okay, is what we're going to implement. And for convenience, we're going to just call it a spectral convolution layer. Okay. So recall what we just learned before the break. We first do the Fourier transform, right? Forward Fourier transform, decompose into the frequency components, and then compute some linear transformation of the frequency components. And as a result, we get, some transformed signal. And then we're going to be applying the inverse of the inverse Fourier transform to generate the output. Oops. So here we are, spectral convolution 1D layer. So it is comprised of this thing called the self.weights, okay? And the self.weights is basically where we store the learnable Fourier coefficients, right? Remember, whatever input signal comes in, we map it to the Fourier domain, And then in the free domain, we, compute the linear combination of the, Fourier components, right? Fourier coefficients. So that transformation is what's stored in the self.weights. And this is kind of a PyTorch way of defining custom weights. So whenever you want to build your own, new neural network layer, okay, as opposed to the ones that are already predefined, like so far we use nn.linear, nn.conv1d, those are the predefined layers. But if you, for whatever reason, if you want to define your own layer, this is how you could do, right? nn.parameter, and then basically specify the number of, values. Now, the actual fun is in this, forward function, right? So similar to how you would define an entire neural network, when you define a single layer, you basically have the structure. You have the initialization function, and then you have the forward function. So the forward function is where the actual calculation happens. And if you look at the implementation, yeah, like I said, it's pretty simple at the end of the day, right? You first apply the Fourier transform, and then this is the usual perceptron, where you multiply weights to the input, and that's how you define the output. And then on that output, we just apply the inverse of RFFT to produce the final output. Okay. So in terms of what comes in and what comes out, so the input to the spectral convolution layer is a tensor of the size batch by channels by signal length. Okay, so batch is the number of samples in one batch. And then the channels define how many, variables essentially you have. So if the input contains a variability and let's say density, then you have two channels, right? If you have more variables, then you have channels, right? So that's what defines the number of channels. And then the signal length is basically the length of the physical domain in this case, because by the way, we're going to be, applying this to a 1D physics problem. If it is a 2D physics problem, then it's going to be width by height, right? Instead of the signal length. And then the RFFT function in PyTorch will automatically detect the dimension and then perform the Fourier transform, in that case 2D Fourier transform. Okay. But in our case here, we're just using a one-dimensional signal. And then as a result of the Fourier transform, we're going to have the same number of batches. The batch size doesn't change, obviously. The number of channels doesn't change, obviously, right? The only thing that changes is now instead of the entire signal length, we saw that for 128 hertz signal, we have up to 64 hertz. So we're going to have a half of the signal length stored in the Fourier coefficient. So X underscore FT is essentially the collection of, Fourier transformed input. Now the output, out FT, is defined as, here's a fun one. Here's a thing called the EINSUM, EINSUM function. The EINSUM function is what's called the Einstein summation. So I don't know how many of you are familiar with the term Einstein summation. It's a notation that was first proposed by Einstein, the physicist. And whenever you have a summation of values with complex, with lots of indices, Einstein's summation notation basically suggests that any repeating indices are the indices that are summed over. So if you're from mechanical engineering background, for example, you probably have seen that in solid mechanics or, places like that where, instead of writing the full summation symbol with, all the indices, you can get rid of the summation symbol and then just down. Now in PyTorch, what that einsum does is to let you define any arbitrary tensor multiplication. So inside of einsum, we have BIX comma IOX, and then we have the arrow and BOX, okay? So what happens is we have two tensors coming in to the summation, and then as a result of the Einstein summation, we produce one tensor, okay? The first tensor we're going to call, we're going to index the first tensor, B, I, and X. So B here stands for the number of batch. I stands for the number of channels. And then X stands for the number of, grids in the x-axis. So as a matter of fact, our input was the number of batches, number of channels, and then the signal length, right? So basically we're indexing, indexing them using BIX, okay? And then IOX is essentially the weight parameter that we're learning. And then the index of this weight parameter is that we have the number of channels, which is indexed by I. And then we have the number of outputs, which is indexed by O. And then we have the signal length X. And then we're taking the dot product, okay? Because, the Einstein summation notation, we have the repeating index I, right? So we're taking the dot product along the direction of I indices. So the summation happens along I. And as a result of that, we produce a tensor that has the number of batches by the number of outputs by the signal length, okay? Does that sort of make sense? So we have a tensor A, and then the index of the tensor A is B I X, and then we have a tensor B, and then the index of the tensor B is I O X, and then by Einstein notation, we are taking the summation of I, in the direction of I, to define the final output, let's say Y, tensor Y, indexed by B, O, and X. Okay. So that mathematical expression is essentially what's, defined in that torch.einsum. So to give you another example, let's say if you have Aij multiplied by Bjk, and then take the summation across J, and if that's what defines Cik, okay? This, by the way, is the usual matrix multiplication, right? So we have a matrix A and matrix B. We're taking the matrix multiplication, right? So in that way, Ik is over here, Jj repeating. So we're taking the summation over J. So according to the Einstein notation, this is simply A, Ij, B, Jk. Okay. Einstein was lazy, so he didn't want to put too much, too many sigmas. So this is the usual matrix multiplication. And this in PyTorch can be written as ein sum of ij, jk, arrow, ik. Okay. So this whole notation may look, not so friendly, but once you get used to it, this is an extremely convenient, function using which you can define pretty much everything related to tensor multiplication. Okay. So, once you get used to it, the moment when you see this, you will notice that, this is basically a matrix multiplication. Or how about this? Ein sum ij and kj ik. Can you guess what that is? So ik, those are the indices defining the output. And then the repeating index that's not on the output side is where the summation happens. So we're multiplying the column of the first matrix against the column of the second matrix. So this is equivalent to A times B transpose. Right? Or sorry. Yeah, no, this, yes. A times B transpose. Right? Because if you do the transpose, column will become a row, right? And then the multiplication happens in that way. So that's really what the ein sum function does. So now that the ein sum makes sense, let's go back to this code over here. So we have essentially, so B, O, X, those are the indices that shows up at the outputs on the output side. And then the only index that's repeating and not showing up in the output is I. So we are basically taking the multiplication on the second axis of the first tensor and then the first axis of the second tensor. And this is that, element-wise multiplication part, right? So remember in the definition of Fourier Fourier neural operator layer, we had this linear transformation R, where you start from, some number of Fourier coefficients to, after the transformation, we have some other number of Fourier coefficients, right? So in this illustration, we have 4 components to 2 components. And then R is basically, in this case, 4x2 matrix. Sorry, 2x4 matrix, right? That maps the 4 components to 2 components. So that's essentially what we're doing over there. Okay. And then, after that linear transformation, we're applying the inverse of the RFFT to construct it, to map it back to the original signal domain. So what's really happening is, this parameter over here, self.weights, the self.weights over here, self.weights is multiplied by the Fourier coefficients coming from the input signal, right? According to that Einstein summation notation. is essentially what's happening. And then it's basically a linear transformation of the frequency, components, the Fourier coefficients. And then in that way, you can define the spectral convolution 1D layer. So that, yes, I did not explain. So thanks for reminding. So in the definition of the spectral convolution 1D layer, we have the argument called the number of frequencies. Okay. And then that number of frequencies is, stored as a self.n freq. And basically, in the forward function, we're keeping the number of frequencies. Okay, so we're truncating the number of frequencies in that way. Yes. Oh, yeah. So the way so that so let me first explain that the number of weights, okay, weight is a tensor that is comprised of I times, so I by O by number of frequencies, the signal length, okay? So I is the number of, the number of input signals. So, number of input channels, okay? So again, if you have, let's say, permeability and density, then I is going to be 2. You have 2 channels. You can have as many channels as you want, right? So that arbitrary number of channels is what's represented by in underscore channels. And then for the output, you may want to produce a different number of outputs than the number of input channels. So we have a separate variable for the output channels. So we have some I by O by number of frequency as a tensor. And when we initialize the learnable parameter, we randomly generate a number of the size I by O by number of frequencies. So that's what this torch.rand stands for. Now the scaling is, remember the Gloro initialization and the He initialization, where the idea was to initialize the weights so that the norm of the weight is kind of adequate, that the variance of the input and the variance of output is maintained pretty much the same. So that is something that we talked about already. So that initialization is essentially what's happening over here. Number of channels on the input, number of channels on the output. You multiply them, and that's roughly the scaling, right, of the weight values. So we're compensating that by dividing by the input channels by times the output channel. That the initial distribution of weight has an adequate size, right? So that it doesn't exaggerate the input variance and the output variance. Yes. So right now we're implementing this in an arbitrary dimension, arbitrary number of channels on the input, arbitrary number of channels in the output. We're defining it as a generic form. And then later, when we actually design the architecture, we're going to specify the number of inputs and the number of outputs. Similar to the NN linear layer. NN linear layer requires the number of input channels and the number of output channels, right? So we're taking the same design principle. Yeah. Yes. Yeah. Well, like I just mentioned, we're just randomly initializing the weights, right? We're randomly initializing the weight, and because the random number that we're using is going to be in between 0 and 1, roughly this torch.rand, this tensor, this random tensor, will scale the input by the factor of number of input channels by times number of output channels, right? So to compensate that, we're dividing it, by that much. But if you, for example, use something else like the normal distribution with different variants, then the scaling factor is going to be different. But I'm going to need to, do the math to figure out what the right scale might be. Yeah, that's what's happening. I just explained to you. This is the weight. You know, so this is what probably you missed the lecture about the weight initialization. You want to initialize the weights in such a way that the input data distribution, the variance of the input data distribution is roughly the same as the variance of the output data distribution. Okay. So that, whenever you apply the weighted sum, you can maintain the variance of the distribution pretty much the same across. Otherwise, as you go deeper into the layers, the signals will grow and the amplitude will go crazy. Or, if the weights are too large, too small, then, the variance of the distribution is going to, shrink and dwindle to 0. Roughly the same variance. So that's why we're scaling, the random numbers by that factor. Okay. Yeah. Um, so this is the PyTorch way of saying, the random numbers that we're generating over here are the ones that will serve as the model parameter in the neural network. So those are the ones that are trainable. So when you define your own custom layer, and when you want to specify which of the variables, so like inside of this class, we have lots of variables. There's a variable name in underscore channel, out underscore channel, and frix. We have scale, we have weights. Out of those, the self.weight is the variable that we want to train. Everything else is a constant. So to say that, we put everything inside of an end-up parameter. And that's how we say that, oh, this particular variable over here is going to be the one that we're going to train. We're going to figure out. Everything else is constant. Yeah. Yeah, so these are the things that we're going to tune, okay, during the training. All right, any other questions? Okay, so now that we have the spectral conv layer defined, the Fourier neural operator layer, okay, is simply a stack of a bunch of spectral conv layers alongside some conv 1D, which correspond to the bottom path over here. So we have the spectral conv 1D layer for this, and then we have the usual 1D convolution layer applied to the original signal, and then we add them up to produce the final output. So here you can see that in the initialization, we have 4 convolution layers. So 4 spectral 1D convolution layers. So this is the Fourier transform that we just defined. And then we have the 4 skip connection layers. So you can see that we are 4 repeating blocks of Fourier neural operators. So in the forward function, what happens is, look at the this part over here. What happens is, for a given input X, we go into 2 routes, one that goes through the bottom, and then one that goes on the top, the Fourier part, right? So the same input goes through the skip connection layer and the convolution, spectral convolution layer. The result of those 2 pathways are added together to define the output. And that output is what goes into the activation layer. So this is a 1 copy of a Fourier neural operator, that diagram that we saw in the PowerPoint slide, right? And then basically we're repeating that 4 times. So we have 4 stacks of FNO layers, right? And then before and after the FNO layers is basically just a pre-processing. A pre-processing that's defined by some linear layer. So we have FC0, which is a linear layer. So in our case here, we're going to see the application where the input to FNO is a signal with 2 channels, okay? And then the Fourier operator is supposed to produce 1 channel output. So 2 channel input comes in, and then width over here is the number of, I mean, literally the width of a perceptron, right? So, the number of hidden neurons, is what I meant. So self.width is the width of the Fourier, neural operator layer. And then the 2 channel input is going to be pre-processed and then transformed into the width. Okay, so that's the number of channels. And then the Fourier neural operator part, FNO layers, we're going to just keep the same number of channels, input and output, for the simplicity. Of course, you can change it to, something more sophisticated, right? But in this example, we're just going to keep, repeating the same width. So the width of the network doesn't change. And then at the end, that whatever width that is, that might be, we're projected to the 128-dimensional space, and then finally to the 1-dimensional output, scalar output. And that's essentially, the design of the FNO, neural network. Now, using this, we're going to apply it to what's called the 1D Burgers equation. So Burgers equation is another kind of a canonical PDE that a lot of people use when they want to test numerical solvers and things like that. The equation itself looks like this, where we have the convection term and then the diffusion term. So we have the convection term where we describe the transport of the matter, and then the term where the quantity is is diffused to the surrounding areas. So that is the physical process that we're interested in. Now I have a pre-generated set of numerical simulations. So we have 1D Burger equation simulation with a varying number, varying number of cases. So here, for example, so here's the plot. Actually, the output red is a little different. So again, we started from this black curve at time t equals to 0. And then after a certain time t, the distribution of the values changed to this red curve. It became a little smoother, right, compared to the initial configuration. Let me show you one more example. So this is another, training sample. We started from a lot more complicated configuration initially. And then after, certain time step t, because of the diffusion and the advection process, that original black curve has deformed into this red curve over here. So we have lots of such data, okay, in the data set, which is obtained by solving a direct numerical simulation according to that exact PDE. And our goal, obviously, is to train the neural operator to make such a prediction. So here I split the data set into 70% for training, 15% for validation. So validation data set is for the monitoring of the training process. And then another 15% of the data set aside for the final evaluation of the result. So in terms of the total number, the training data set has 1,433 samples. And then the validation and test set have roughly 300 samples. Was there a question? Yes. What about the data set? Yeah, so originally we have total 2,000 samples, okay? Each of the sample has, 256 by 3. 206 indicate the grid size. So it's a 1D signal. And then the one-dimensional space is divided into 256 nodes, right? To discretize that space. And then 3, why is it 3 actually? Oh, oh yeah, sorry. X is the position vector. So yeah, so we have 3 channels. The first channel is the position X. The second channel is the initial condition. The third channel is the fluid configuration after certain time t. So the first 2 channels are going to be the input to our neural network. The last channel is going to be the output prediction. Told you, pay attention. We're dividing the one-dimensional space into 256 grid points. Yeah. Just told you like 30 seconds ago. Loss function we're going to define. So bear with me. We're not there yet. So finally, here we define the model. FNO1D is what we just defined. So it's a bunch of 4 spectral convolutions and skip connections, right? So that's that. And then we set the width to be 64. So again, that's equivalent to the number of hidden neurons, right? And then we have the usual optimizer. over here, we introduced this thing called the learning rate scheduler. So this might be something new, but this is a very common technique. So learning rate scheduler, we start from some fixed learning rate. And then this step LR scheduler, step learning rate scheduler, what it does is every certain number of steps, it'll multiply this factor gamma to the learning rate so that you start from a large learning rate, you make an aggressive search, and then after a certain number of iterations, you reduce the learning rate, the search step length, and then fine tune the search so that you can converge to a better solution. So that's usually what people do, and it's called the learning rate scheduler. If you want to ignore this, feel free to ignore it. Actually, the learning rate scheduler in this particular example is not that critical, but I thought I would introduce the learning rate scheduler so that you know how to use it. And then the rest is really what we've been seeing, right? So we have the for loop going over some number of iterations, and then we make a model prediction and then compute the loss over here. And the loss obviously is defined as the mean square error. So like I said, the first two channels in the training data is our input to the model. And then the last channel is going to be the ground truth output, which gets compared against the prediction. And then loss.backward, optimizer.step. I mean, we've been doing this for many times already. And that's really the training of the neural operator. The rest of the code is basically for plotting the result every now and then. So in terms of the training process, there's nothing specific, special about the neural operator. It's all about the design of the architecture. And then we saw that, Fourier transform was used for the definition of the convolution layer. And then we constructed a, neural operator accordingly. But then the actual training process, there's nothing special. So it's running right now. The convergence is quick. And then after the convergence, you'll be able to see, how the neural operator performs on the test data set. So, test data set, roughly 15% of the samples we set aside. And then for those unseen, side examples, we're basically testing if the neural operator will be able to make an accurate prediction. And for this 1D burger scenario, it does a fairly good job. I can show you if once the training is done. But that's really what it is. So while this is running, what time is it right now? Oh, we're already over time. So I guess we should wrap up. I wish the training. Yeah, never mind. You can run it at home, and you should be able to see the result after the training is done. So I think really the key takeaway message is that the Fourier formulation for modeling that kernel. So in the typical neural networks, those kernels were a discrete set of numbers. It was a matrix, kernel matrix. And then we trained the kernel matrix, and those were the unknowns that we wanted to figure out during the training. Versus in the Fourier neural operator, we, instead of using the discrete kernel, now we have a continuous kernel modeled as the Fourier coefficients. And that's something that we're figuring out by training the model, is really the key takeaway message. And other than that, it's pretty much the same as the usual neural network training. You have some set of inputs and some set of outputs, and you're figuring out the input to output mapping. There's nothing, terribly new about it. something just popped up. So here for one, given case, the black curve over here is the ground truth. And then the neural operator does a sort of okay job, but it's only after 20 iterations. So after running more iterations, you'll actually see more accurate results. But yeah, for any given input signal, you should be able to throw that into the neural operator, and then the neural operator will make a prediction uh, in terms of what's going to happen after time. Yeah. So again, neural networks can only do things that they're trained for. Yeah, artificial intelligence is not that intelligent, right? It can only do the thing that it is trained for. So if it is trained for the task of predicting the fluid configuration after time t, that's the task that it can do. If you want to predict after time 2t or 3t or 4t, it's not going to do a very good job because obviously that's not the task that it is trained for. So, you know, it's a downside, I guess. But to be fair, I mean, if there's a prediction model that can extrapolate that much, then you're not going to need to stay here because at that point, AI is going to, take over the humanity, and then, you wouldn't need to do any of those. So. So again, you can, use the you can introduce the physics informed laws during the training of the neural operator. So since we know the equation of the Burgers, since we know the Burgers equation, we can, construct a physics informed laws during the training. And in that way, you can make it, a little more generalizable. But again, if you train the task on predicting after time t, and that's the task that, it is trained for. And there's going to be a limit in terms of how far you can generalize. So. Well, again, we talked about the advantage of neural operator, throughout the whole day. So um, compared to the, sorry, what's the question? So again, like we discussed throughout the day, the neural operators, um, it's beyond just, image to image mapping or signal to signal mapping, right? Um, the immediate advantage of a neural operator compared to the usual neural networks is, like I said earlier, we can handle the continuous signals as opposed to the pixel discretized signals, right? Is one advantage. Other advantages may include that, once this is combined with the physics informed laws, then you can inform certain, physics equations. There's a lot of degree of freedom in terms of how you could implement the neural operator. But the most prominent contribution of this work is, like I said, it allows you to handle the continuous function to a continuous function mapping as opposed to the pixel to pixel mapping. Again, like I said, there's an overhead of doing the Fourier transform. So yes, by being, enabling the continuous function to continuous function mapping, you're giving up a little bit of computational speed, right? But there's no free lunch in the real world. So if you achieve something, you have to give up, some other things. So in this case, the trade-off is going to be the ability to handle the continuous function versus the computational overhead. All right. No, this is more expensive because we're doing things like Fourier transform. Yeah. Okay. We're already way past